In this video, we will learn about fundamental concepts related to cross-validation. We'll begin with an overview of cross-validation, followed by different approaches to statistical cross-validation, and then finish up with different approaches to empirical cross-validation. So let's start with that overview. So cross-validation is a key component of what we refer to as true predictive analytics. So as a review, predictive analytics are part of the continuum of data analytics, which includes descriptive analytics, predictive analytics, and prescriptive analytics. So we can define predictive analytics in terms of the fact that they predict what will happen in the future based on available data, and then verify how accurate those predictions are based on new, future, fresh, or unseen data. So we can think about the predictive analytics process as a two-phase process, where in phase one, we have our initial sample of data or our past data, and then we train our model on that data. And our model could be a simple linear regression model, a multiple linear regression model, and then it could also include more advanced types of supervised statistical learning models and machine learning models or algorithms. So when you hear the word concept train model, it really is very broad in terms of what it might include. So again, we take our past data, we train the model on it, and then we get our model parameter estimates, the results, how well the model fit the data, and so forth. And then in phase two, we get new data or fresh unseen data from that same underlying population as that initial past sample of data, and then we take our trained model and we apply that model to the new data and we get predictions. And then we can evaluate the model's performance and prediction accuracy with this phase two data, this new data. And this phase two really represents what we consider to be cross-validation. In phase one, we're validating the initial model, and in phase two, we are cross-validating that model with a new sample of data from the same underlying population. So what is the definition of cross-validation? Well, we can define cross-validation as a process by which we determine how well a model generalizes to another sample drawn from the same population. A related term is cross-validity. As Cascio and Guinness defined in their 2005 book, cross-validity refers to whether the regression coefficients derived from one sample can predict outcomes to the same degree in the population as a whole or in other samples drawn from the same population. So what is the purpose of cross-validation? When our goal is to make predictions based on our model, we want to improve prediction accuracy when the model is applied to fresh or unseen data from that same population. And this is going to require minimizing prediction errors. When we estimate a model based on a single sample of data, we run the risk of overfitting the model to the data from that sample, which may hurt how well the model predicts when we apply it to fresh data. In other words, when we're overfitting the model, we might be making a model that performs too well with regard to the idiosyncrasies of that single sample of data, meaning that it won't generalize very well to other samples from that same population. So cross-validation helps us understand how well our model predicts when applied to other data from the same underlying population. You can think of cross-validation as an approach to evaluating model performance. So there's different types of cross-validation, and we will focus on two general types of cross-validation. First, statistical cross-validation, and then second, empirical cross-validation. So let's start with statistical cross-validation. So statistical cross-validation bypasses the need to acquire data from additional sample from the underlying population. So this approach involves computing adjusted statistics that can be used to estimate how well the model would perform if we were to acquire data from another sample. But again, we're not acquiring data from another sample. We're computing these based on the initial original sample of data. And so you can imagine that this has some limitations because we're not actually applying the model then to an unseen sample of data that the model was not trained on initially. So there are several ways in which we can perform statistical cross-validation. For instance, we could compute the adjusted R-square value, the squared cross-validity, or the cross-validity. So let's dive into each one of these. So the adjusted R squared value and the squared cross-validity can be interpreted together when making judgments about the cross-validity of a model. So often we'll use both of these types of statistical cross-validation indicators. Again, that's the adjusted R squared and the squared cross-validity. We can use those in tandem to make judgments about the cross-validity of a model. So again, let's dive into these specific types of statistical cross-validation. So let's start with that adjusted R squared. So here is the formula for the adjusted R squared. And you can see that N represents the sample size, K represents the number of predictor variables in the model, and R squared unadjusted is represented by R squared and then subscript unadjust. And so here I've color-coded these for you where the sample size N is green, the number of predictor variables in the model, K, is purple, and the blue corresponds to the R squared unadjusted. So as you can see, we're plugging our unadjusted R squared into the model, and then we're essentially penalizing it based on the sample size and the number of predictor variables we have in that model. So here's an example where we have a sample size equal to 200, which you can see here, we've replaced that in the initial formula or equation above. And then the number of predictor variables in this hypothetical model is 3. And then let's imagine that our unadjusted R squared value is 0.25, which you see represented here. If we plug those values into our formula, we get an adjusted R squared value of 0.24. So the unadjusted R squared of 0.25, which you see here, is downwardly adjusted to 2.24 when we have a sample size of 203 predictor variables in our model. Now let's see what happens when we take that initial sample size and we decrease it from 200 to 100. And you can see I've replaced that in the formula, but we keep the number of predictor variables in the model constant or the same at 3. Here you can see that the R squared adjusted value decreases further from 0.24 to 0.23 when we decrease that sample size from 200 to 100, but keep the number of predictor variables at 3. So again, this is illustrating that idea that as our sample size decreases, we are penalizing or shrinking our amount of variance that we would explain with the model. In other words, the R squared value. So let's hold the sample size constant, and now let's increase the number of predictor variables in the model from 3 to 6. And we're keeping, again, the unadjusted R squared value the same at 0.25. So when we keep the sample size the same at 100, but increase the number of predictor variables to 6, we further reduce the adjusted R squared from 0.23 to 0.20. So to sum up, the adjusted R squared corrects for the model's effective sample size relative to the number of predictor variables in the model. So consequently, the adjusted R squared results in a lower estimate than the unadjusted R squared, which makes it a better approximation of model fit and reflects the sample-specific variance explained by the predictor variables in relation to the outcome variable when we compare it to the unadjusted R squared. So what's nice about adjusted R squared is that most statistical software programs provide the adjusted R squared value automatically for example, linear regression models. Now let's move on to the squared cross-validity. So the squared cross-validity formula is as appears here, where again, N represents the sample size, K is the number of predictor variables in the model, but this time we have R squared adjusted in the model instead of R squared unadjusted. And so here you can see the formula here, and this formula will do something similar to the adjusted R squared, where the smaller our sample size is and the larger the number of predictor variables is, it's going to downwardly adjust or shrink our R squared value, which in this case will end up being referred to as the squared cross-validity. Okay? And as before, the sample size is represented with an N in green, the number of predictor variables is represented with K in purple, and then blue represents the adjusted R squared instead of that unadjusted R squared that we saw with the initial adjusted R squared formula. So let's plug in this hypothetical example where we imagine that our sample size is 200, the number of predictor variables in the model is 3, and that our adjusted R squared value is 0.25. So if we plug those values into the formula, we get a squared cross-validity of 0.24. So the adjusted R squared of 0.25 that we plugged into the model becomes the squared cross-validity of 0.24 when the sample size is 200 and the number of predictor variables in the model is 3. Now imagine that we keep the number of predictor variables the same at 3, and then we decrease the sample size from that 200 to 75. And we'll see what happens in terms of how reducing the sample size further reduces our squared cross-validity. And so here you can see that the cross-validity shrinks from 0.24 when our sample size was equal to 200 to 0.23 when it's equal to 75, but the number of predictor variables remain the same, remain constant. Lastly, let's take a look at when we keep that sample size the same at 75, but we increase the number of predictor variables in the model from 3 to 6. Here you can see that when the sample size remains at 75, but the number of predictor variables increases to 6, the squared cross-validity further shrinks from 0.23 to 0.21. So like the adjusted R squared, the squared cross-validity corrects for the model's effective sample size and the number of predictor variables in the model, such that the squared cross-validity is downwardly adjusted with smaller sample sizes and a larger number of predictor variables. So most statistical software programs, from my experience, don't readily provide the squared cross-validity, so this is a statistic that you may need to compute on your own. Finally, let's talk about cross-validity. So here's the formula for cross-validity here, and it should look pretty familiar. Again, we have the sample size represented with the green N, the number of predictor variables in the model represented with the purple K, and then the adjusted R squared value represented in blue. Now, the cross-validity is just the square root of the squared cross-validity. And so you can see that with underneath the square root sign here, it's just our squared cross-validity formula. If we take the square root of it, then we have simply the cross-validity. So now let's move on to the empirical approaches to cross-validation. So empirical cross-validation differs from statistical cross-validation in that it requires that we acquire data from an additional sample from the underlying population, or that we split our original or initial sample if it's sufficiently large. Examples of empirical cross-validation include the holdout method of cross-validation, which is really the traditional empirical approach to cross-validation, k-fold cross-validation, and leave one out cross-validation. And we'll look into each one of these examples in just a moment. So let's start with that holdout method of cross-validation. So with the holdout method, we have our initial sample of data, and then we'll typically, if it's large enough, we will randomly split that initial sample of data into a training data set and a test data set. And so again, if we have a large enough initial sample of data, we can split it into a training data set and a test data set, and our test data set is going to serve as our holdout sample, hence the concept or the term holdout method. Now, a common way that we split the initial data sample is the 80-20 approach, where we randomly assign 80% of the cases from the initial sample to the training data set and 20% to the test data set. Now, alternatively, if we have a smaller sample size of data, we may need to start with our initial data sample, train the model on that sample, and then later on we'll collect more data from the underlying population, and that second sample will serve as our test data set. So after we have split our data, we're ready to train the model on the training data set. And the training data set is used again to train or to estimate that initial model. And then we evaluate that initial model that we trained or estimated against the test data set data. So we take that trained model and evaluate its performance using the test data set. And so this completes that cross-validation process, where essentially in the first step where we train the model, we're validating the model. In the second step, we are cross-validating that model. So now let's talk about k-fold cross-validation, which goes a step further than the holdout method. So similar to the holdout method, we can start with our initial sample of data, and then we can perform some kind of split, maybe the 80%, 20% split, where 80% of the cases from the initial sample are randomly assigned to be in a training data set, and the remaining 20% in a test data set. K-fold cross-validation then differs, though, because after we randomly split the data into our training data set and test data set, we then are going to go through this K-fold process to actually cross-validate and validate our model in order to train our model initially. So the training data set is going to be randomly split into K samples, and the K samples will be equal to K folds. Okay? So K is the placeholder that represents the number of samples. And you can have different variations on K-fold cross-validation where you could do 5 folds, 10 folds, etc. So in each fold, the model is trained on the pooled data from K-1 samples, and the remaining sample is treated as a holdout sample to cross-validate or validate the model. So again, we take our initial K samples and then K-1 samples, so we're leaving out one of those samples, and then we're going to train the model on all the remaining samples, and then we're going to cross-validate against that sample that we left out initially. Now this process is going to repeat until all K samples have served as the cross-validation sample. The models estimated across the K folds are then going to be synthesized such that the estimated errors are synthesized. So the errors could be root mean square, could be root mean squared error. It could also be R squared values, for example. So again, the models estimated across the K folds are going to be synthesized, and that means that they're going to be, the estimated errors are going to be synthesized, which often means averaged to reach a model performance estimate for the final model. So the final model's parameter estimates can then be estimated using all the available data from our training data set. So after that, we can then extend the K-fold cross-validation process by taking the final trained model and evaluating its performance when applied to the unseen or fresh test data set. Because remember, the initial model was not trained using any of that test data. That was kind of the last holdout sample there. So let's walk through an example of K-fold cross-validation, and specifically this will be 5-fold cross-validation, where we have 5 samples or 5 folds that we split our initial training data set into when we're trying to cross-validate the model. So it's going to look very similar to what we saw before, but now we have a concrete number of samples. So we have 1, 2, 3, 4, 5 samples that we randomly split our training data set into in order to train the model. So in the first fold, we would take the first 4 samples, pool them together, train our model, and then we would take that model and use the holdout sample, that 5th sample, to validate it or cross-validate it. We then repeat the same thing where we take samples 1, 2, 3, and 5, we train the model in those 4 samples, and then for that holdout sample, we validate or cross-validate that trained model. Then we repeat it where for samples 1, 2, 4, and 5, we pool those together, we train our model based on that pooled sample, and then with that trained model, we cross-validate or validate it against that holdout sample, which was sample 3. And then do the same thing with sample 1, 3, 4, and 5. We pool those together, train our model, and then we take that trained model and validate or cross-validate it against sample 2, which was the holdout sample. And then lastly, we take samples 2, 3, 4, and 5. We pool those together. We train our model based off that pooled sample, and then we take that trained model and then we validate or cross-validate it in terms of how it performs against that first sample, which was our holdout sample in that fold. So again, we work through 5 different folds here. 1, 2, 3, 4, 5, hence the name 5-fold cross-validation. And so once we've done that, we're ready to then apply our trained model to the test data if we want to go this further step, and then we can evaluate the model's data, the model's performance rather, against fresh unseen data which came from that test data set that we didn't use at all to train the model initially. So finally, let's talk about the empirical cross-validation approach called leave one out cross-validation. Now, this is just essentially k-fold cross-validation taken to its logical extreme. And what I mean by that is that it's going to be k-fold cross-validation where k is going to be equal to the sample size in our training data set. So what does that mean? Well, that means that the number of folds k is going to be equal to the sample size n, such that in each fold, the model is trained on all the data except one case. And this process is repeated until every case has served as the holdout validation sample. And as you can imagine, this could be computationally intensive if you have really, really large samples of data that you're working with. Nonetheless, this is another approach. So to sum up, we learned about the traditional empirical cross-validation approach called the holdout method. We then learned about k-fold cross-validation. And then lastly, we just learned about leave one out cross-validation. And all three of those are types of empirical cross-validation. And so in this video, we started with that overview of what is the purpose of cross-validation, how does it fit into predictive analytics, and then we distinguished between different approaches to statistical cross-validation versus empirical cross-validation. So here are the references that I cited throughout the slides here. And this wraps up the video in which we covered the fundamentals of cross-validation.